Okay, so for these notes, we're still in Unit 2, Compounds and Composition notes, but we are kind of transitioning into a new topic, so we still obviously will be doing lots of cake and ice cream problems, but we're going to look at like if all our problems that we were working with in cake and ice cream in dimensional analysis were compounds of things, so we elaborated on our knowledge of dimensional analysis, and so then we're working with like big molecules of things like FeSO4 and C6H12O6, and so I kind of wanted to get into how those molecules come about. So right now this set of notes are going to be over chemical reactions. So we've talked a little bit about chemical reactions with like names and formulas and balancing the formulas, but we haven't really talked about how to predict the outcome of reactions between different types of molecules. So that's what we're going to be looking at here. So we talked about this with physical and chemical changes or properties. And so physical changes are things, remember, that like don't change the chemical structure of the molecule or whatever you're working with. So if we like rip a paper in half, is it still paper? Yes. If we boil water and it goes from a liquid to a gas, is it still water? Yes. But sometimes things don't happen that way, and those are chemical reactions when it actually does change what compounds are formed. So evidences of chemical reactions include the first one, color changes. So a really obvious color change is one that we're familiar with is rusting. So rusting, we know, is a chemical change, and one way we can know that is because the color changes. Okay, the second one is evolution of gas. So this one, don't be confused if like, oh, well, water goes from a liquid to a gas. This one is more talking about when we're combining elements. So let's say we had two solids. And we combine those and we get a gas of some sort. Okay, so since we didn't start with a gas and we ended with the gas, that's an indication of a chemical change. A third evidence of a chemical reaction is the formation of a solid which we will abbreviate PPT. And a precipitate is like if we is just something solid. So this would be like if we combined two liquids and then we get a solid. So then this solid would be a precipitate because we didn't start off with a solid. Okay, and then the third one is a change in energy. Okay, so this change in energy, these types of energies that could be changed or exhibited, the change could be shown through heat. So if there is a emission of heat or a lack of heat in the reaction, if there is light energy, and if there's some type of chemical energy. Okay, so if we witness any of those are evidence to a chemical reaction, a reaction between two chemicals that formed a new chemical. Like always, we'll rewrite it, but we should know it by now. For equations, the reactants on the left products on the right. And they're just a representation of chemical reactions. And so here we also talked about balancing those. Okay. So these reactions that we're going to be talking about, so the reactions that we're talking about right now are going to be reactions in aqueous solutions. And aqueous solutions are just where water is the solvent. So these reactions are taking place in water. When we get to examples, we'll talk about, like, we won't mention water, but we just know it happens in water. Okay? So the first category, I guess we could say, of reactions are precipitate reactions. Okay? And I'm going to highlight that so we can find it easier later on. So in precipitate reactions, the first type is single replacement. Also known as, you might see it like this sometimes, substitution. And single displacement. Okay, so in single replacement or substitution or displacement, exactly what it sounds like happens. So it's the synthesis reaction between two or more different elements where one atom takes the place of another. So one atom just takes the place of another. This is the general form for this. So instead of using actual elements, we'll just use A and B. So if we have A plus elements B and C, if just one of these is being replaced, we'll have AC plus B. Okay, because this A replaced this single B right here. There's only one element replacing that. So it's a single replacement because there's only one element that is doing the replacing. Okay, these reactions are not reversible. So there might be some reactions that can continue forward and backward, and we draw a little arrow like that because they can go back and forth, but these are not that type of reaction. They cannot go back and forth like that. Okay, so we know that reactions can be made of different types of elements or from different groups. So if the element is metal, it may take the place of the metal in the compound. So that's just saying that, say, let me switch colors. Let's say if this one is a metal, let's go with, let's say we have lithium right here. And this one is sodium and sodium chloride, okay? Which is good old table salt. So if this reaction were to happen, these two metals would switch places because metals typically have similar properties. So then we just have lithium chloride and sodium. Okay. Moving on down. In the same, for the same reasoning, if the element is a nonmetal, it may take the place of the nonmetal. Okay, so notice that it says may. It doesn't say always. It just says may. That's what it typically will do, but we'll definitely see reactions where that doesn't happen. So don't bank on that. But it will be typical for it to take the place of the metal if it's a metal. So, there are obviously different types of elements on the periodic table that will be more reactive. We've already kind of talked about those. So that is just called activity. And so if they have an increased activity, that means that they are going to form reactions or go through reactions more easily. And if they have a decreased activity rate, then reactions will go less frequently or slowly. So the activity is just the likelihood of reaction occurring. So for metallic elements, those metals, will refer to the activity series of metals to see if reaction will occur. So I'm not expecting you to memorize the entire chart, but you should kind of know a couple of them that are at the top of the activity list, the couple metals. So the ones with increased activity at the top of the list are lithium, rubidium, potassium, barium, among others. So these are at the top of the list. These are metals that will be more likely to form reactions because they have a high activity rate. So there's a big long list on page 272 in your book. So you can go look at that. It will be helpful for you to look at that. But definitely memorize like a couple of these because they are important to know. But is the periodic table only made of metallic elements? Of course not. So let's talk about the halogen elements. The halogens, which is group 7A. Okay, and this is where you're going to refer to your handy dandy periodic table to see if the reaction will occur. Because the activity decreases as you move down the group of halogens. So I want you to get out your handy dandy periodic table because can be marking that. That will be something very important for you to have on there, that the halogens that are located in group 7A, so the ones that begin with fluorine, chlorine, bromine, iodine, and then the other ones that aren't as fun to say, they decrease as you move down. So fluorine and chlorine have the highest because they're at the top of the list. So all I want you to do on your periodic table, let's say this is your column 7A, and this is fluorine, this is chlorine, and then around the elements, here's neon, and here's argon, and here's oxygen over here, and sulfur. I want you to just draw an arrow that goes like that, and then maybe at the top you can fit an activity. So the activity of them decreases as you go down the periodic table. Their likelihood of reacting goes down as you go down the periodic table. So an example of a single replacement reaction is chlorine gas plus 2 potassium bromides yields what? So here, our chlorine, is our chlorine a metal or a non-metal? Chlorine is a non-metal. It's a gas. And we have potassium. Is that a metal or a non-metal? That is a metal. And then we have bromine, which is also a halogen. So it's also a gas, so a non-metal here. So since this single atom right here is a non-metal, it's going to replace this non-metal right here. So then this reaction would yield potassium chloride now plus Br2. Okay, and let's double check that our reaction is balanced. So we have 2 chlorines right here. And how many chlorines do we have right here? 1. So we're going to fix that just by adding a 2 there. And then we have 2 chlorines, 2 chlorines. We have 2 potassiums, and we have 2 bromines. Okay, bromine gas right here. And that is our single replacement because this single nonmetal replaced this nonmetal over here. Okay, moving on to the next type of reaction, a double replacement reaction. So like what we just did, but double. Okay, I'm going to highlight that so we can find it easier. Okay, so in this case, the two aqueous reactants switch cations. And cations, remember, are they the positive or the negative metal? They are the positive metal. So again, the general formula for this one is going to be AB plus XY yields AY plus XB. So here you'll see we still have the A and the X in the front, and then just the B and the Y have swapped. Okay, so I'm just going to draw a little arrow. Those ones have swapped. And an example of this is going to be if you had PbNO3 aqueous plus Ki, that's an I, aqueous, meaning it's in water, yields. So in here, just the two aqueous reactants, this is the aqueous reactant and this is the aqueous reactant. These two are going to switch the cations that they're with. So in this, the cations, remember, are the positive metals. So here's our positive metal, and here's our positive metal. So they're just going to switch. So that we get Pb I2 plus KNO3. And you might be wondering how we knew this was I2. I2, or I, and then bromine and oxygen and nitrogen, those are some of the typical diatomic elements. So we know that anytime I is just going to be I2 down here in a reaction because that's what it's going to form. Okay, so other examples of these are acid-base, neutralization, reactions. So if we have an acid and we're trying to make it neutral, we'd be putting in a base. Or if we have a base and we're trying to make it neutral, we'd be putting in an acid. So for this one, if we did another example, we could do HCl in an aqueous solution. And HCl is hydrochloric acid, which obviously is an acid. And then we have NaOH in an aqueous solution. And NaOH is a very strong base. And so if we were to run this reaction, our two aqueous forms here, the chlorine and the hydroxide, are going to switch. And then our cation is going to be hydrogen, now with this OH. And NaCl. Okay, so this right here is otherwise known as good old H2O. So we get H2O plus sodium chloride. So we know that's a liquid, and this is an aqueous. So from this reaction of hydrochloric acid and sodium hydroxide, we actually get water and sodium chloride. Okay, so that is it for the precipitate reactions. And we'll move on to a different type of reactions called redox reactions. Okay, and there are three types of redox reactions that we are going to talk about. The first type is a synthesis reaction, and otherwise known as a combination reaction. So the word synthesis just means to make something. So in this kind of reaction, the reactants combine to form one product. So they make one product. That's really important. They form one single product. So the general formula for this is A plus X yields AX. So from the two single reactants, we get one compound. Okay, an example of this would be two moles of SB plus 3 moles of I2 yields what? It would yield, we just combine them, so it would yield SB, since that's our metal, and I3, because the charge of antimony over here is 3 plus, so that crisscross method comes down. So we get SbI3, and then we have to make sure our equation is balanced. So here we have 2 antimonies, here we just have 1, and here we have 6 antimonies, and right here we have 2, or 3 rather. So this could be fixed easily by putting a 2 there. So now that we have 2 antimonies and 6 iodines. Okay, let's do another example of a synthesis reaction. So if we have 2 Mg, and that's a solid, plus O2, and we know that that is a gas, that would yield MgO. And it's just O, not O2, because the 2 plus charge and the 2 minus charge here cancel out. So we'll just have one of each of those. And MgO is a solid. So now we have to go back and balance the equation. So here we have 2 magnesiums and 2 oxygens. And here we just have one of each. So this can easily be balanced by just putting a 2 there. Okay. So our next type of reaction that we will talk about is a decomposition reaction. So in a decomposition reaction, like if you talk about something decomposing, like an organic once living thing, if something is decomposing, it's basically getting broken down. Same thing here in a decomposition reaction, a single reactant breaks down into 2 or more products. So if something is breaking down, this kind of reaction is the opposite of a synthesis reaction. Because in synthesis, we're building things, we're making things, but here we are breaking them down. So the general formula for this is, a single reactant, AB, yields or breaks down into 2 or more products. So it starts off as AB and then it yields A plus B. So we started off as one thing right here and we get 1, 2. So let's work out an example of this type of reaction, a decomposition where something gets broken down. So if we have 2 H2O, and that's all we have, so we have our 1, yields, that's going to get broken down into H2 and O2. And we know it's H2 because the charge of oxygen is 2 negative, so that 2 gets crisscrossed. That's where that 2 came from, was up here. And so when it gets separated, it's H2, and then it has to be O2 because it's diatomic, and it can't just be oxygen. Now let's go back and make sure these are balanced. So on the reactant side, how many hydrogens do we have? We have 4 hydrogens. Right here we just have 2. So let's smack a 2 in front of it and see what happens. We have 4 hydrogens, and 2 oxygens and 2 oxygens. So this is our balanced equation. Now let's do another example of a decomposition reaction. So in this example, we have 2 NaCl, sodium chlorides, and that's going to yield Na and chloride. And let's do the crisscross method to figure out our charges. So Na has a charge of 1 plus, and chlorine has a charge of 1 minus. So when we crisscross them, we get just 1 down here. But chlorine can't ever be easy. It's a diatomic element also. So it has to be CO or Cl2, just like O2 has to be O2. And now let's go back and balance our equation. So over here we have 2 NAs. Over here we just have 1. So we'll smack a 2 in front and see if that works for us. Now we have 2 NAs, 2 NAs, 2 chlorides, 2 chlorines. Okay, and then the third type of redox reaction is going to be a combustion reaction. And there's another word you might be familiar with just because it's a common word that people use. And it is an exothermic reaction. So if we think back to our bio terms, exo means outside, and therm means temperature or heat. So an exothermic really literally releases heat outside. So it's an exothermic reaction in which a hydrocarbon rapidly combines with oxygen to produce CO2 or carbon dioxide and water. This can also be known as burning. So a fire is an example of a combustion reaction. It's supposed to say produce here. To produce those two things. Okay, and so a fire is hot because it's an exothermic reaction where heat is being released. Okay, so the general form for a combustion reaction, since we know the reactants and the products, it's not just going to be like a random A element or B element. The general form for this one is C for carbon, and then we don't know how many atoms of carbon, H, but we don't know how many atoms because it could be a different ratio, plus oxygen yields CO2 plus H2O. Okay, so if you think about it, what is one of the ways that you can like put out a fire? If you put a blanket or, a fire retardant blanket or throw water on it, it extinguishes the combustion reaction because it no longer has access to oxygen. Or if you put a fire in a vacuum where there is no oxygen, it's not going to continue because a fire needs this oxygen gas in order to happen. So if we wanted to look at an example of a combustion reaction, we could look down here. And if we had, I'll go back up so we can see the general form. If we had C3, H8, so those can vary because those are the X and the Y, so they can vary, and that's a gas, plus 5O2, 5 oxygen gas, that's going to yield CO2 plus H2O. Okay, but the only thing we have to figure out is the balanced equation. So down here we have, or up here, we have 3 carbons. Down here we just have 1. So a quick fix to that would be to put a 3 here. And then we have 8 hydrogens over here. And how many hydrogens do we have right here? Just 2. So a quick fix would be to put a 4 there. And then let's go back and check. See if we're good. So we have 3 carbons. We have 3 carbons. We have 8 hydrogens. We have 8 hydrogens. We have 10 oxygens. And here we have 6 oxygens right here, plus these 4 right here, which is 10, which is what we had right here. Okay, so this is our balanced equation for this combustion reaction. Okay, so you can kind of start seeing where everything that we've talked about so far with the crisscross method, with the stoichiometry, with the balancing equations, it's kind of all tying in together. Because, hello, like I've been saying this entire time, chemistry and science really does build on itself. So we have to make sure that we're getting caught up and staying caught up with the things that we're going over, so that we can, when we continue on and work on things in class and in the lab, then it will make sense and we'll be able to do it.